Oxidation corrosion damage mechanisms as a part of high-temperature corrosion greater than 400 degrees Fahrenheit or 204 degrees Celsius. Description of oxidation corrosion damage mechanisms based on API 571. Oxygen reacts with carbon steel and other alloys at high temperature, converting the metal to oxide scale. Number B. It is most often present as oxygen is in the surrounding air, approximately 20%, used for combustion in fired heaters and boilers. Here's a detailed description of oxidation damage, starting with an introduction. Introduction. Oxidation damage refers to the deterioration or degradation of materials, tissues, or surfaces caused by exposure to oxidative agents such as oxygen, ozone, or reactive oxygen species, or ROS. In biological systems, oxidation damage often results from an imbalance between the production of ROS and the body's ability to neutralize these reactive molecules, leading to damage of cells, DNA, proteins, and lipids. This process is associated with aging, inflammatory conditions, and various diseases, including neurodegenerative disorders and cancer. In materials science, oxidation damage can cause corrosion, weakening, discoloration, or failure of metals, polymers, or other materials when they react with environmental oxidants. Overall, oxidation damage compromises structural integrity and function across biological and non-biological systems. Detailed explanation of oxidation damage. Number 1 is mechanism of oxidation. At its core, oxidation involves the loss of electrons from a molecule, atom, or ion. When a substance is exposed to an oxidizing agent, it undergoes a chemical reaction where electrons are transferred, resulting in chemical modifications. In biological systems, this often involves reactive oxygen species or ROS such as superoxide anion or O2, hydrogen peroxide or H2O2, hydroxyl radicals or OH, and singlet oxygen or O2. These highly reactive molecules can readily interact with cellular components. Number 2 is sources of oxidation. The first sources of oxidation is from environmental factors. Exposure to oxygen, ozone, pollutants, ultraviolet or UV radiation, and chemicals can initiate oxidation in materials or tissues. The second sources of oxidation is from metabolic processes. In living organisms, normal metabolic activities produce ROS as byproducts, especially in mitochondria during ATP production. The third sources of oxidation is from external factors. Smoking, radiation, and pollution increase oxidative stress, overwhelming natural antioxidant defenses. Number 3 of detailed explanation of oxidation damage is biological oxidation damage. In biological tissues, oxidation damage primarily affects lipids, proteins, and nucleic acids. Lipid peroxidation, ROS attack unsaturated fatty acids in cell membranes, leading to chain reactions that produce lipid peroxides. This compromises membrane integrity, fluidity, and function, resulting in increased permeability and cell death. Protein oxidation, oxidative modifications of amino acid side chains, formation of carbonyl groups, cross-linking, or fragmentation impair enzyme activity, structural proteins, and signaling pathways. DNA damage, ROS can cause base modifications, strand breaks, and mutations in DNA, which may lead to cellular dysfunction, apoptosis, or carcinogenesis. Number 4 of detailed explanation of oxidation damage is material oxidation damage. In non-biological systems, oxidation results in corrosion and degradation. Metal corrosion, oxidation of metals like iron produces rust, iron oxide, weakening structural components. Polymer degradation, oxidative reactions cause polymers to become brittle, discolored, or cracked. Surface deterioration, oxidation can lead to surface pitting, loss of gloss, and reduced mechanical strength of materials. Number 5 of detailed explanation of oxidation damage is factors influencing oxidation damage. Presence of catalysts, transition metals such as iron and copper catalyze ROS formation via Fenton reactions. Antioxidant defenses, the body's endogenous antioxidants, such as glutathione, superoxide dismutase, catalase, neutralize ROS and mitigate damage. Environmental conditions, higher temperatures, UV exposure, and humidity accelerate oxidation processes. Material composition, the chemical structure influences susceptibility, unsaturated bonds are more prone to oxidation. Number 6 of detailed explanation of oxidation damage is consequences and significance. Oxidation damage contributes to aging and the development of numerous diseases, including cancer, cardiovascular diseases, neurodegenerative disorders, like Alzheimer's and Parkinson's, and inflammatory conditions. In materials, oxidation leads to reduced lifespan, safety hazards, and increased maintenance costs. Number 7 of detailed explanation of oxidation damage is prevention and mitigation. Strategies include the use of antioxidants, both natural and synthetic, protective coatings, controlled environments, and material treatments to inhibit oxidation processes. Oxidation description summary. In essence, oxidation damage is a complex, multifaceted process driven by chemical reactions involving oxidants that modify molecules and materials, often resulting in functional deterioration. Its understanding is vital across disciplines to develop better ways to prevent, delay, or repair oxidative damage, thereby improving health outcomes and material longevity. Oxidation Corrosion Damage Mechanisms based on API 571, Number A. All iron-based materials including carbon steel and low-alloy steels, both cast and wrought. Number B. All 300 series SS, 400 series SS and nickel-base alloys also oxidize to varying degrees, depending on composition and temperature. Certainly. Here is a comprehensive, detailed overview of the materials affected by oxidation damage. Affected materials of oxidation damage, a detailed overview. Oxidation damage impacts a wide range of materials across biological and non-biological systems. The susceptibility and damage mechanisms vary depending on the material's composition, structure, and environment. Here is an in-depth affected material examination of these materials. Number 1 is biological materials. Number A of biological materials is lipids, cell membranes and lipoproteins. Lipids, cell membranes and lipoproteins. Description: lipids, especially polyunsaturated fatty acids or PUFAs in cell membranes and lipoproteins, are highly susceptible to oxidative attack. Lipids damage: lipid peroxidation leads to the formation of lipid radicals, aldehydes, like malondialdehyde, and other reactive products. This causes loss of membrane fluidity, increased permeability, disruption of membrane-bound proteins, cell lysis or apoptosis. Contributes to atherosclerosis via modification of LDL particles. Number B of biological materials is proteins. Proteins description: proteins contain amino acids with susceptible side chains such as cysteine, methionine, tyrosine. Proteins damage: oxidation causes carbonyl formation, cross-linking and aggregation, enzyme inactivation, structural protein denaturation, impairment of cellular functions and signaling. Number C of biological materials is DNA and nucleic acids. DNA and nucleic acids description: DNA bases and sugar phosphate backbones are vulnerable to oxidative modifications. DNA and nucleic acids damage results in base modifications, such as 8-oxo-DG, strand breaks, mutations, potential carcinogenesis and cell death. Number D of biological materials is cellular organelles. Mitochondria, particularly vulnerable due to ROS generation during respiration. Endoplasmic reticulum and other organelles, damage impairs protein folding in cellular metabolism. Number 2 of oxidation damage mechanisms affected material is non-biological materials. Number A of non-biological materials is metals and alloys. Iron, steel, and cast iron. Iron, steel, and cast iron type of damage: rust formation, iron oxides. Iron, steel, and cast iron process, oxidation of Fe to Fe superscript 2 and Fe superscript 3, forming hydrated iron oxides. Iron, steel, and cast iron impact, structural weakening, surface pitting, and failure. Aluminum, copper, and zinc. Aluminum, copper, and zinc form oxides or hydroxides that can lead to corrosion and surface degradation. Number B, of non-biological materials is polymers and plastics. Polymers and plastics description: many synthetic polymers contain susceptible bonds or additives. Polymers and plastics damage. Chain scission leading to embrittlement. Discoloration. Loss of mechanical strength. Surface cracking. Surface cracking polymers and plastics examples: polyethylene, polypropylene, PVC. Number C, of non-biological materials is ceramics and glass. Ceramics and glass description: generally resistant but can suffer oxidative degradation at high temperatures or in reactive environments. Ceramics and glass damage, surface corrosion, erosion, or pitting under oxidative conditions. Number D, of non-biological materials is organic materials, such as wood, leather, textiles. Organic materials description: organic materials contain cellulose, proteins, or lipids. Organic materials damage, oxidation causes discoloration, brittleness, and loss of flexibility. Number 3, of oxidation affected material is environmental materials. Number A, of environmental materials is paints and coatings. Paints and coatings damage, oxidation of pigments and binders leads to fading, chalking, and peeling. Number B, of environmental materials is rubber and elastomers. Rubber and elastomers damage, oxidative cross-linking or chain scission causes cracking, hardening, or softening. Number 4, of oxidation affected material is electronic components. Electronic components description: metals, semiconductors, and insulating materials. Electronic components damage, oxidation of contact surfaces reduces conductivity, causes corrosion of circuit elements, and degrades performance. Summary table of affected materials. For material type is biological lipids, the specific materials is cell membranes, lipoproteins, then the typical oxidation damage is lipid peroxidation, then the consequences is membrane damage, cell death, atherosclerosis. For material type is proteins, the specific materials is enzymes, structural proteins, then the typical oxidation damage is oxidation of amino acids, then the consequences is enzyme inactivation, aggregation. For material type is DNA, the specific materials is nucleic acids, then the typical oxidation damage is base modifications, strand breaks, then the consequences is mutations, apoptosis. For material type is metals, such as iron, copper, the specific materials is steel, aluminum, zinc, then the typical oxidation damage is rust, corrosion, then the consequences is structural failure, aesthetic decay. For material type is polymers, the specific materials is plastics, rubbers, then the typical oxidation damage is chain scission, embrittlement, then the consequences is loss of strength, cracking. For material type is ceramics and glass, the specific materials is porcelain, silica-based materials, then the typical oxidation damage is surface erosion, pitting, then the consequences is surface degradation. For material type is organic materials, the specific materials is wood, leather, textiles, then the typical oxidation damage is discoloration, brittleness, then the consequences is material deterioration. For material type is coatings and paints, the specific materials is paints, varnishes, then the typical oxidation damage is fading, chalking, then the consequences is aesthetic and protective failure. For material type is electronic components, the specific materials is circuit boards, metals contacts, then the typical oxidation damage is corrosion, loss of conductivity, then the consequences is device malfunction. Oxidation damage mechanisms affected material. Final remarks: understanding which materials are affected by oxidation damage and how they deteriorate is vital for developing protective strategies, selecting materials for specific environments, and designing maintenance protocols. The susceptibility varies widely, but oxidative processes generally lead to weakening, discoloration, loss of functionality, and structural failure across diverse materials. Oxidation damage mechanisms. Critical factors based on API 571, Number A, the primary factors affecting high-temperature oxidation are metal temperature and alloy composition. Number B, oxidation of carbon steel begins to become significant above about 1000 degrees Fahrenheit or 538 degrees Celsius. Rates of metal loss increase with increasing temperature. Number C, in general, the resistance of carbon steel and other alloys is determined by the chromium content of the material. Increasing chromium levels produce a more protective oxide scale. The 300 series SS are resistant to scaling up to about 1500 degrees Fahrenheit or 816 degrees Celsius. See Table 4.8 in API 571. Number D, the presence of water vapor can significantly accelerate oxidation rates of some steels including 9Cr, 1MO, reference, F. Dettenwanger et al., the influence of C, W and water vapor on the oxidation behavior of 9Cr steels, paper number 01151, NACE International, Houston, Texas, 2001. Certainly. Here's a comprehensive, detailed explanation of the critical factors of oxidation damage. Critical factors influencing oxidation damage, a detailed overview. Oxidation damage is a complex process influenced by multiple interrelated factors. Understanding these factors is essential for predicting, preventing, or mitigating oxidative deterioration in materials and biological systems. Here is an in-depth analysis of the key critical factors of oxidation damage. Number 1 is presence of oxidizing agents. Number A, of presence of oxidizing agents is oxygen concentration. Oxygen concentration role, the primary oxidant in most biological and non-biological systems. Oxygen concentration impact, higher oxygen levels increase the likelihood and rate of oxidation reactions. Oxygen concentration details, in biological systems, oxygen tension varies across tissues, in materials, oxygen availability influences corrosion rates. Number B, of presence of oxidizing agents is reactive oxygen species or ROS. Reactive oxygen species examples, superoxide anion or O2, hydroxyl radicals or OH, hydrogen peroxide or H2O2, singlet oxygen or O2. Reactive oxygen species impact, these highly reactive intermediates accelerate oxidation, especially in biological tissues. Reactive oxygen species generation, produced via metabolic processes, environmental exposure, or catalyzed reactions, e.g., metal catalysts. Number C, of presence of oxidizing agents is other oxidants. Other oxidants examples, ozone or O3, nitrogen oxides or NOx, peroxides. Other oxidants impact, contribute to oxidative stress and material degradation. Number 2 of critical factors of oxidation damage is catalysts and transition metals. Number A, of catalysts and transition metals is metal ions, such as Fe, Cu, Co, Mn. Metal ions role, catalyze oxidation via Fenton and Haber-Weiss reactions. Metal ions mechanism, transition metals can cycle between oxidation states, generating ROS from peroxides. Metal ions impact, accelerate lipid peroxidation, protein oxidation, and corrosion processes. Number B, of catalysts and transition metals is metal particles and surfaces. Metal particles and surfaces example, iron rusting, copper corrosion. Metal particles and surfaces impact, surface catalysis enhances oxidation rates. Number 3 of critical factors of oxidation damage is material composition and structure. Number A, of material composition and structure is chemical structure. Chemical structure unsaturated bonds, lipids and polymers with double bonds are more prone to oxidation. Chemical structure presence of susceptible functional groups, amino acids like cysteine, methionine, phenolic groups. Number B, of material composition and structure is microstructure. Porosity. Increased porosity allows oxygen and ROS penetration. Surface area. Higher surface area accelerate. Number C, of material composition and structure is protective coatings and barriers. Absence or degradation of protective layers exposes underlying material to oxidants. Number 4, of the key critical factors of oxidation damage is environmental conditions. Number A, of environmental conditions is temperature. Temperature effect. Elevated temperatures increase kinetic energy, thus accelerating oxidation reactions. Temperature implication. High temperature environments, such as combustion engines, industrial processes, exhibit faster oxidation. Number B, of environmental conditions is humidity and moisture. Humidity and moisture impact. Moisture facilitates electrochemical corrosion and hydrolytic reactions. Humidity and moisture in biological systems. Water acts as a medium for ROS diffusion and reactions. Number C, of environmental conditions is light exposure. Light exposure UV and visible light can generate ROS such as singlet oxygen and promote photooxidation. Light exposure materials, photodegradation of polymers and coatings. Number D, of environmental conditions is pH levels. pH levels, acidic or alkaline conditions, influence oxidation kinetics. pH levels example, corrosion of metals accelerates in acidic environments. Number 5, of the key critical factors of oxidation damage is antioxidant defense and inhibitors. Number A, of antioxidant defense and inhibitors is endogenous antioxidants or biological systems. Endogenous antioxidants or biological systems examples, glutathione, superoxide dismutase, catalase, vitamin C, vitamin E. Endogenous antioxidants or biological systems role, neutralize ROS, inhibit chain reactions. Number B, of antioxidant defense and inhibitors is external antioxidants and inhibitors. External antioxidants and inhibitors use in materials, antioxidant additives in plastics or coatings. External antioxidants and inhibitors impact, reduce oxidation rate by scavenging free radicals or chelating metal catalysts. Number 6, of the key critical factors of oxidation damage is time and exposure duration. Time and exposure duration cumulative effect, longer exposure leads to more extensive oxidation. Time and exposure duration kinetics, oxidation often follows a time-dependent pattern, with initial lag phases followed by rapid deterioration. Number 7, of the key critical factors of oxidation damage is mechanical and physical stress. Number A, of mechanical and physical stress is mechanical damage. Mechanical damage impact, cracks, scratches, or deformation expose fresh surfaces to oxidants. Mechanical damage result, accelerates localized oxidation, e.g., pitting corrosion. Number B, of mechanical and physical stress is thermal cycling. Thermal cycling impact, expansion and contraction cause microcracks, increasing oxidation susceptibility. Number 8, of the key critical factors of oxidation damage is pH and electrochemical conditions. pH and electrochemical conditions, corrosive environments, pH extremes promote oxidation in metals. pH and electrochemical conditions, electrochemical potential, high potentials favor oxidation reactions. Here are summary of the oxidation damage mechanisms critical factors. When the critical factors is oxidant availability, with description is oxygen, reactive oxygen species or ROS, chemicals, then, the effect on oxidation damage is accelerates oxidation reactions. When the critical factors is catalysts, with description is transition metals, surfaces, then, the effect on oxidation damage is catalyze reactive oxygen species or ROS formation and transfer electrons. When the critical factors is material composition, with description is unsaturated bonds, functional groups, then, the effect on oxidation damage is determined susceptibility. When the critical factors is environmental conditions, with description is temperature, humidity, light, pH, then, the effect on oxidation damage is modulates reaction rates. When the critical factors is antioxidants inhibitors, with description is endogenous/exogenous compounds, then, the effect on oxidation damage is mitigate oxidation. When the critical factors is exposure duration, with description is time of contact, then, the effect on oxidation damage is cumulative damage. When the critical factors is mechanical stress, with description is cracks, deformation, then, the effect on oxidation damage is exposes fresh surfaces. Final remarks of oxidation damage mechanisms. Critical factors. The progression and severity of oxidation damage depend on a delicate interplay of these factors. Controlling or modifying these variables, such as reducing oxygen exposure, removing catalysts, applying protective coatings, or using antioxidants, can significantly delay or prevent oxidative deterioration. Oxidation damage mechanisms. Affected units or equipment. Based on API 571, oxidation occurs in fired heaters and boilers as well as other combustion equipment, piping and equipment that operates in high-temperature environments when metal temperatures exceed about 1000 degrees Fahrenheit or 538 degrees Celsius. Certainly. Here's a comprehensive, detailed overview of the units or equipment affected by oxidation damage, including the types of equipment, their susceptibility, and the specific nature of oxidation-related deterioration. Affected units or equipment of oxidation damage. A detailed overview. Oxidation damage can impair a wide range of equipment and units across various industries. The impact often leads to reduced efficiency, safety hazards, increased maintenance costs, and eventual equipment failure. Below is an in-depth analysis categorized by industry and equipment type. Number 1 of oxidation damage mechanisms. Affected units or equipment is mechanical and structural equipment. Number A of mechanical and structural equipment is piping systems and valves. Piping systems and valves. Materials affected: steel, cast iron, aluminum, copper, plastics. Piping systems and valves. Oxidation effects: rust formation, iron oxides, leading to pitting and thinning. Corrosion-induced leaks and blockages. Valve seat and seal degradation. Number B of mechanical and structural equipment is pressure vessels and storage tanks. Pressure vessels and storage tanks. Materials: steel, aluminum alloys, composites. Pressure vessels and storage tanks. Oxidation effects: surface corrosion weakening structural integrity. Pitting corrosion causing leaks or catastrophic failure. Coating degradation exposing the underlying metal. Number C of mechanical and structural equipment is rotating equipment, such as pumps, turbines, compressors. Rotating equipment. Susceptibility: bearings, shafts, blades. Rotating equipment effects: corrosion-induced fatigue. Surface pitting leading to imbalance. Reduced lifespan and increased maintenance. Number D of mechanical and structural equipment is structural frames and supports. Structural frames and supports. Materials: steel, reinforced concrete. Structural frames and supports. Effects: rust expansion causing cracking, spalling, and loss of load-bearing capacity. Number 2 of oxidation damage mechanisms. Affected units or equipment is electrical and electronic equipment. Number A of electrical and electronic equipment is electrical contacts and connectors. Electrical contacts and connectors. Materials: copper, silver, gold-plated contacts. Electrical contacts and connectors. Effects: oxidation reduces conductivity. Increased contact resistance causes overheating. Number B of electrical and electronic equipment is circuit boards and components. Circuit boards and components. Materials: metal traces, solder joints. Circuit boards and components. Effects: corrosion leads to open circuits. Short circuits and failure of electronic systems. Number C of electrical and electronic equipment is motors and generators. Motors and generators. Components affected: bearings, windings, commutators. Motors and generators. Effects: corrosion causes insulation failure. Reduced efficiency and risk of failure. Number 3 of oxidation damage mechanisms affected units or equipment is hydraulic and pneumatic systems. Number A of hydraulic and pneumatic systems is hydraulic lines and actuators. Hydraulic lines and actuators materials, steel, aluminum, rubber hoses. Hydraulic lines and actuators effects include corrosion of metal parts leading to leaks, contamination and damage to seals. Number B of hydraulic and pneumatic systems is compressed air systems. Compressed air systems effects, rust in air tanks and pipelines reduces efficiency and introduces contaminants. Number 4 of oxidation damage mechanisms affected units or equipment is process equipment and industrial units. Number A of process equipment and industrial units is heat exchangers. Heat exchangers materials, copper, aluminum, steel tubes. Heat exchangers effects includes fouling due to rust deposits, reduced heat transfer efficiency. Number B of process equipment and industrial units is reactors and tanks. Reactors and tanks materials, steel, glass-lined steel. Reactors and tanks effects includes corrosion causes contamination and structural failure. Increased maintenance and downtime. Number C of process equipment and industrial units is filtration and separation units. Filtration and separation units effects, corrosion leads to material degradation, compromising process integrity. Number 5 of oxidation damage mechanisms affected units or equipment is storage and handling equipment. Number A of storage and handling equipment is warehouse and storage tanks. Warehouse and storage tanks materials, steel, plastic. Warehouse and storage tanks effects includes rusting of steel tanks, contamination and leaks. Number B of storage and handling equipment is transport vehicles. Transport vehicles examples, trucks, ships, rail cars. Transport vehicles effects, corrosion of chassis, cargo holds, tanks, and pipelines. Number 6 of oxidation damage mechanisms affected units or equipment is infrastructure and civil engineering units. Number A of infrastructure and civil engineering units is bridges and support structures. Bridges and support structures materials, reinforced concrete, steel. Bridges and support structures effects, rust expansion causes cracking and spalling, threatening safety. Number B of infrastructure and civil engineering units is pipelines and ducts. Pipelines and ducts materials, steel, cast iron. Pipelines and ducts effects, pitting corrosion causes leaks, blockages, and failures. Number 7 of oxidation affected units or equipment is biological and medical equipment. Number A of biological and medical equipment is implants and prosthetics. Implants and prosthetics materials, titanium, stainless steel. Implants and prosthetics effects, oxidative corrosion can lead to material degradation and biological incompatibility. Number B of biological and medical equipment is laboratory instruments. Laboratory instruments effects, corrosion of metal parts affects precision and sterilization. Number 8 of oxidation damage mechanisms affected units or equipment is marine and coastal equipment. Number A of marine and coastal equipment is ship hulls and underwater structures. Ship hulls and underwater structures materials, steel, composites. Ship hulls and underwater structures effects, severe corrosion, especially in seawater, leading to structural failure. Number B of marine and coastal equipment is offshore platforms. Offshore platforms effects, corrosion of support beams, pipelines, and equipment due to saltwater exposure. Here are the summary table of oxidation damage mechanisms affected units or equipment. In the industry or field is oil gas, then, the equipment or units are pipelines, tanks, valves, then, the nature of oxidation damage will occur are such as rust, pitting, corrosion, and then, the consequences are leaks, failures, safety hazards. If the industry or field is power generation, then, the equipment or units are turbines, boilers, generators, then, the nature of oxidation damage will occur are such as corrosion, deposits, and then, the consequences are reduced efficiency, breakdowns. If the industry or field is manufacturing, then, the equipment or units are hydraulic systems, machinery, then, the nature of oxidation damage will occur are such as surface rust, component degradation, and then, the consequences are downtime, maintenance costs. If the industry or field is marine, then, the equipment or units are ship hulls, offshore rigs, then, the nature of oxidation damage will occur are such as saltwater corrosion, and then, the consequences are structural failure, safety risks. If the industry or field is electronics, then, the equipment or units are circuit boards, connectors, then, the nature of oxidation damage will occur are such as oxidation, conductivity loss, and then, the consequences are malfunctions, failures. If the industry or field is civil infrastructure, then, the equipment or units are bridges, supports, then, the nature of oxidation damage will occur are such as steel corrosion, cracking, and then, the consequences are structural integrity risk. If the industry or field is healthcare, then, the equipment or units are medical implants, then, the nature of oxidation damage will occur are such as material degradation, and then, the consequences are device failure, biocompatibility issues. Final remarks of oxidation damage mechanisms affected units or equipment. Oxidation damage affects virtually every type of unit or equipment that involves metals, polymers, or other susceptible materials exposed to oxidative environments. Its effects include corrosion, pitting, cracking, loss of mechanical strength, electrical failures, and safety hazards. Preventative measures such as coatings, corrosion inhibitors, cathodic protection, and material selection are crucial to mitigate these effects. Appearance or morphology of oxidation damage mechanisms based on API 571, Number A, most alloys, including carbon steels and low alloy steels, suffer general thinning due to oxidation. Usually, the component will be covered on the outside surface with an oxide scale, depending on the temperature and exposure time. See Figure 4:111. Oxidation of a carbon steel nut on a stainless steel stud at 1300 degrees Fahrenheit or 704 degrees Celsius. See Figure 4:112. Oxidation of a carbon steel grid from a sulfur reactor. See Figure 4:113. Oxidation of the OD of a carbon steel furnace transfer line. Number B, 300 series SS and nickel alloys generally have a very thin dark scale unless exposed to extremely high temperatures where metal loss rates are excessive. Certainly. Here's a comprehensive, detailed explanation of the appearance or morphology of oxidation damage, covering how oxidation manifests at various scales and in different materials. How oxidation manifests at various scales and in different materials. Appearance and morphology of oxidation damage, a detailed overview. Oxidation damage manifests through distinct physical and structural changes at the macro, micro, and nano scales. The morphology of oxidation is heavily dependent on the material involved, environmental conditions, and the duration of exposure. Understanding these morphological features is critical for diagnosing, assessing, and preventing oxidation-related deterioration. Number 1 is general characteristics of oxidation morphology. Color changes, reddish-brown rust in iron-based materials, black oxides in some metals, discoloration in polymers. Surface roughness, increased roughness due to corrosion products, pitting, or spalling. Cracking and spalling, fracture of oxide layers or underlying material. Pitting and voids, localized corrosion leading to cavities. Layer formation, development of oxide scales or films with distinct structures. Number 2 is morphology in metallic materials. Number A, of morphology in metallic materials is oxide scales and films. Oxide scales and films appearance, usually appear as flaky, crusty, or smooth layers. Oxide scales and films coloration, ranges from black, brown, orange, to dull gray, depending on oxide type. Oxide scales and film structure includes protective oxide layers, thin, adherent, uniform films such as aluminum oxide in aluminum alloys. Non-protective layers, thick, porous, flaky, or spalled layers such as iron rust. Number B, of morphology in metallic materials is pitting corrosion. Pitting corrosion morphology, small, deep cavities or holes penetrating the metal surface. Pitting corrosion features includes: usually initiate at inclusions, impurities, or surface defects. Characterized by sharp or rounded cavity edges. Often asymmetric and localized. Number C, of morphology in metallic materials is uniform corrosion. Uniform corrosion surface appearance, roughened, matte, or matte-like surface with uneven thinning. Uniform corrosion scale morphology, often exhibits a granular or flaky oxide layer. Number D, of morphology in metallic materials is crevice and exfoliation corrosion. Crevice and exfoliation corrosion appearance, flaking or peeling oxide layers, sometimes delaminate. Crevice and exfoliation corrosion morphology, stratified oxide layers separating from the substrate, creating layered or exfoliated textures. Number 3 is morphology in nonmetallic materials. Number A, of morphology in nonmetallic materials is polymers and plastics. Polymers and plastics color changes, discoloration from transparent or original color to yellow, brown, or black. Polymers and plastic surface degradation includes: cracking, due to chain scission or embrittlement. Surface blistering or bubbling, from oxidative cross-linking or degradation. Surface roughening, micro-roughness or pitting from chain scission. Number B, of morphology in nonmetallic materials is ceramics. Ceramics appearance, oxidation often causes color changes, e.g., darker hues. Ceramic surface morphology, formation of microcracks or glaze deterioration. Number 4 is microstructural and nanostructural features. Number A, of microstructural and nanostructural features is pitting and localized corrosion. Pitting and localized corrosion microscale, small cavities, often with sharp or rounded profiles. Pitting and localized corrosion nanostructure, oxide layers may exhibit amorphous or crystalline phases, with grain boundary precipitates. Number B, of microstructural and nanostructural features is layered oxide scales. Layered oxide scales morphology, multilayered structures with varying grain sizes and porosities. Layered oxide scales cracks and voids, often develop within the oxide layer due to thermal stresses or volume changes. Number C, of microstructural and nanostructural features is spalling and flaking. Spalling and flaking appearance, layers of oxide peel off, exposing fresh metal surface. Spalling and flaking morphology, fragmented or exfoliated sheets. Number 5 is specific examples of morphological features. If material is iron and steel, then, typical oxidation morphology is rust or Fe2O3xH2O, pitting, its decryption is reddish-brown flaky rust, deep pits, spalled layers. If material is aluminum, then, typical oxidation morphology is aluminum oxide or Al2O3 scale, its decryption is thin, adherent, sometimes colorful due to thin film interference, can become porous or flaky. If material is copper, then, typical oxidation morphology is copper oxide or Cu2O, CuO, its decryption is greenish patina or verdigris, rough, flaky surfaces. If material is titanium, then, typical oxidation morphology is dense, adherent oxide, its decryption is thin, protective, smooth layer, may crack under stress. If material is polymers, then, typical oxidation morphology is surface cracks, discoloration, its decryption is microvoids, crazing, or blistering due to oxidative degradation. Number 6 is visual and microscopic features. Macroscopic, surface discoloration, flaking, blistering, pitting, crust formation. Optical microscopy, reveals pits, cracks, spalled layers, and surface roughness. Scanning electron microscopy, SEM detailed images showing oxide layer microstructure, cracks, porosity, and corrosion products. Transmission electron microscopy, TEM nanostructural features of oxide layers, grain boundaries, and precipitates. Number 7 is factors influencing morphology. Type of oxide, protective, dense, adherent, versus non-protective, porous, flaky. Environmental conditions, higher humidity, temperature, or aggressive chemicals lead to more severe and distinct morphologies. Material composition, alloying elements influence oxide structure and appearance. Duration of exposure, longer exposure typically results in thicker, more complex oxide layers with varied morphology. Here are summary table of appearance or morphology of oxidation damage. If appearance or morphology aspect is surface color, the description is visual indicator of oxidation type, then, the typical features is rusty red, black, green patina, discoloration. If appearance or morphology aspect is layer structure, the description is oxide films or scales, then, the typical features is thin, thick, flaky, adherent, porous, layered. If appearance or morphology aspect is cracks and spalls, the description is mechanical failure within oxide or substrate, then, the typical features is cracks, peeling, exfoliation. If appearance or morphology aspect is pitting cavities, the description is localized corrosion, then, the typical features is deep, sharp-edged pits. If appearance or morphology aspect is micro-nano features, the description is internal structure of oxides, then, the typical features is grain boundaries, amorphous/crystalline phases, voids. Appearance or morphology of oxidation damage mechanisms. Final remarks, the morphology of oxidation damage is a critical diagnostic feature. Recognizing these features can help determine the severity, type, and progression of corrosion or oxidation processes, guiding appropriate mitigation strategies. Oxidation damage mechanisms prevention and mitigation based on API 571, Number A, resistance to oxidation is best achieved by upgrading to a more resistant alloy. Number B, chromium is the primary alloying element that affects resistance to oxidation. Other alloying elements, including silicon and aluminum, are effective but their concentrations are limited due to adverse effects on mechanical properties. They are often used in special alloys for applications such as heater supports, burner tips and components for combustion equipment. Certainly. Here's a comprehensive, detailed overview of prevention and mitigation strategies for oxidation damage, covering various methods, materials, and practices across industries. Prevention and mitigation of oxidation damage, a detailed guide. Oxidation, especially corrosion in metals, can lead to structural failure, safety hazards, and increased maintenance costs. Effective prevention and mitigation require understanding the underlying mechanisms and employing suitable strategies at material, design, environmental, and operational levels. Number 1 of prevention and mitigation of oxidation damage is material selection and design strategies. Number A of material selection and design strategies is use of corrosion-resistant materials. Use of corrosion-resistant materials alloying, incorporate elements like chromium, nickel, or molybdenum to form protective oxide layers. Alloying example, stainless steels such as 304, 316 contain chromium, forming a stable, adherent chromium oxide layer. Use of corrosion-resistant materials. Corrosion-resistant alloys, titanium, tantalum, and nickel-based alloys offer excellent oxidation resistance. Use of corrosion-resistant materials. Non-metallic materials, use polymers, ceramics, or composites where metal oxidation is problematic. Number B of material selection and design strategies is protective coatings. Protective coatings. Paints and organic coatings, barrier layers preventing oxygen and moisture contact. Metallic coatings includes metallic coatings. Galvanization, zinc coating on steel offers sacrificial protection. Metallic coatings. Aluminization, aluminum layers form dense oxide scales. Number B of material selection and design strategies is protective coatings. Protective coatings, conversion coatings, phosphating, chromating, or anodizing to enhance corrosion resistance. Protective coatings, ceramic coatings, thermal barrier and oxidation-resistant layers in high-temperature environments. Number C, of material selection and design strategies is design considerations. Minimize crevices, sharp corners, and areas prone to trapping moisture. Ensure proper drainage and ventilation. Use design features that reduce stress concentrations and promote even coating coverage. Number 2 of prevention and mitigation of oxidation damage is environmental control measures. Number A, of environmental control measures is control of humidity and moisture. Use dehumidifiers, desiccants, and climate control in storage and operational environments. Maintain low relative humidity, preferably below 50%, in sensitive areas. Number B, of environmental control measures is control of chemical exposure. Limit exposure to aggressive chemicals, chlorides, sulfates, acids. Use neutral or passivating environments where possible. Number C, of environmental control measures is temperature management. Reduce temperature fluctuations that cause condensation. Use insulation and heating to maintain stable temperatures. Number 3 of prevention and mitigation of oxidation damage is protective coatings and surface treatments. Number A, of protective coatings and surface treatments is application of protective coatings. Regular inspection and maintenance of coatings. Use of high-quality, compatible coating systems tailored to environmental conditions. Employ multi-layer coatings for enhanced protection. Number 4 of prevention and mitigation of oxidation damage is cathodic and anodic protection. Number A, is cathodic protection. Sacrificial anodes, attach zinc, magnesium, or aluminum anodes that corrode preferentially. Impressed current systems, use external power supplies to make the metal surface cathodic. Number B, is anodic protection. Apply a controlled anodic potential to form and maintain protective oxide layers, especially in high-temperature environments. Number 5 of prevention and mitigation of oxidation damage is chemical inhibitors and additives. Number A, of chemical inhibitors and additives is corrosion inhibitors. Organic or inorganic compounds, phosphates, chromates, molybdates, or benzotriazole, BTA. Corrosion inhibitors function, form protective films on metal surfaces or neutralize corrosive agents. Number B, of chemical inhibitors and additives is environmental additives. Use in cooling water, process fluids, or paints to reduce oxidation potential. Number 6 of prevention and mitigation of oxidation damage is maintenance and inspection practices. Number A, of maintenance and inspection practices is regular inspection. Visual checks for signs of oxidation, rust, or coating failure. Use of non-destructive testing or NDT, ultrasonic, eddy current, or radiography. Number B, of maintenance and inspection practices is cleaning and surface preparation. Remove existing corrosion products via brushing, blasting, or chemical cleaning. Proper surface preparation before recoating. Number C, of maintenance and inspection practices is timely repair and recoating. Address damages promptly to prevent spread. Reapply protective layers as needed. Number 7 of prevention and mitigation of oxidation damage is operational best practices. Minimize exposure to moisture, salts, and corrosive environments during operation. Avoid stagnant water or condensation pockets. Implement proper drainage and ventilation systems. Number 8 of prevention and mitigation of oxidation damage is advanced and emerging technologies. Number A, of advanced and emerging technologies is nanocoatings. Superhydrophobic or self-healing coatings that repel water and repair minor damages. Number B, of advanced and emerging technologies is smart coatings. Coatings embedded with sensors to detect early signs of oxidation or corrosion. Number C, of advanced and emerging technologies is corrosion monitoring systems. Use of sensors and data analytics for real-time corrosion detection. Summary table of prevention and mitigation methods. If prevention and mitigation strategy is material selection, its description is use corrosion-resistant alloys or plastics, then, typical application to use it is onto chemical plants, marine structures. If prevention and mitigation strategy is protective coatings, its description is paints, galvanization, anodizing, then, typical application to use it is onto pipelines, bridges, tanks. If prevention and mitigation strategy is environmental control, its description is humidity, chemical exposure management, then, typical application to use it is storage facilities, electronics. If prevention and mitigation strategy is cathodic or anodic protection, its description is sacrificial anodes, impressed current, then, typical application to use it is subsea pipelines, tanks. If prevention and mitigation strategy is chemical inhibitors, its description is corrosion inhibitors in fluids, then, typical application to use it is cooling systems, water treatment. If prevention and mitigation strategy is maintenance inspection, its description is regular cleaning, repairs, then, typical application to use it is industrial equipment, infrastructure. If prevention and mitigation strategy is design optimization, its description is minimize crevices, ensure drainage, then, typical application to use it is structural components, machinery. Oxidation damage mechanisms. Prevention and mitigation. Final remarks. Effective prevention and mitigation of oxidation damage require a multifaceted approach combining material science, environmental control, protective coatings, and maintenance practices. Tailoring strategies to specific environments, materials, and operational conditions maximizes their effectiveness. Oxidation damage mechanisms. Inspection and monitoring. Based on API 571, Number A, process conditions should be monitored for establishing trends of high-temperature equipment where oxidation can occur. Number B, temperatures can be monitored through the use of tube skin thermocouples and/or infrared thermography. Number C, loss in thickness due to oxidation is usually measured using external ultrasonic thickness measurements. Certainly. Here's a comprehensive and detailed overview of inspection and monitoring methods for detecting oxidation damage, covering techniques at various scales, their principles, applications, advantages, and limitations. Inspection and monitoring methods for detecting oxidation damage, a detailed overview. Detecting oxidation damage early is critical for preventing structural failure, extending service life, and planning maintenance. Various inspection and monitoring techniques are employed, ranging from visual inspections to sophisticated non-destructive testing, NDT, methods. The choice depends on the material, extent of expected damage, environment, and accessibility. Inspection and monitoring methods for detecting oxidation damage. Number 1 is visual inspection or VI. Visual inspection principles includes direct observation of surface conditions. Identification of visible signs like rust, discoloration, cracks, spalling, pitting, or blistering. Visual inspection techniques includes handheld visual inspection, using naked eye or magnifying tools. Borescopes and fiberscopes, for internal or hard-to-reach areas. Photographic documentation, for trend analysis over time. Visual inspection advantages includes simple, quick, cost-effective. Immediate feedback. Visual inspection limitations includes limited to surface phenomena. Dependent on inspector expertise. Cannot detect subsurface or internal damage. Inspection and monitoring methods for detecting oxidation damage. Number 2 is ultrasonic testing or UT. Ultrasonic testing principles includes sends high-frequency sound waves into the material. Detects changes in wave reflection caused by corrosion pits, cracks, or thinning. Ultrasonic testing types includes pulse echo, measures the time it takes for echoes to return from flaws or interfaces. Spectral analysis, for thickness measurement. Ultrasonic testing application in oxidation includes detects thinning due to material loss from rust or pitting. Measures the remaining wall thickness. Ultrasonic testing advantages includes accurate, quantitative. Can detect subsurface damage. Ultrasonic testing limitations includes. Requires good surface contact. Less effective on rough or corroded surfaces without proper preparation. Inspection and monitoring methods for detecting oxidation damage. Number 3 is radiographic testing or RT. Radiographic testing principles includes. Uses X-rays or gamma rays to produce images of internal features. Variations in density allow visualization of internal corrosion, voids, or delamination. Radiographic testing application includes. Detect internal rust layers, voids, or delamination within coatings or layered corrosion products. Radiographic testing advantages includes. Provides detailed internal images. Non-contact. Radiographic testing limitations includes. Requires specialized equipment and safety precautions. Limited in complex geometries. Inspection and monitoring methods for detecting oxidation damage. Number 4 is eddy current testing or ECT. Eddy current testing principles includes. Uses electromagnetic induction to detect changes in electrical conductivity or magnetic permeability. Sensitive to surface and near-surface flaws. Eddy current testing application includes. Detects surface rust, corrosion pits, or coating disbondment. Suitable for conductive materials like metals. Eddy current testing advantages includes. Rapid, portable. No need for contact or surface preparation. Eddy current testing limitations includes. Limited penetration depth. Less effective on non-conductive materials. Inspection and monitoring methods for detecting oxidation damage. Number 5 is magnetic particle inspection or MPI. Magnetic particle inspection principles includes. Applies magnetic field to ferromagnetic components. Surface and near-surface flaws disturb magnetic flux, attracting magnetic particles. Magnetic particle inspection application includes. Detects surface breaking cracks and corrosion pits. Magnetic particle inspection advantages includes. Sensitive to surface flaws. Portable and straightforward. Magnetic particle inspection limitations includes. Limited to ferromagnetic materials. Surface preparation required. Inspection and monitoring methods for detecting oxidation damage. Number 6 is liquid particle testing or LPT. Liquid particle testing principles includes. Applies a visible or fluorescent dye penetrant to the surface. Flaw openings allow dye to seep in. Excess dye removed, then a developer reveals indications. Liquid particle testing application includes. Detects surface breaking corrosion pits or cracks. Liquid particle testing advantages includes. Simple, inexpensive. Effective for surface flaws. Liquid particle testing limitations includes. Only detects surface flaws. Requires surface cleaning and preparation. Inspection and monitoring methods for detecting oxidation damage. Number 7 is optical and microscopic techniques. Number A of optical and microscopic techniques is optical microscopy. Examines surface morphology at high magnification. Useful for detailed analysis of rust layers, pitting, and crack propagation. Optical and microscopic techniques. Number B is scanning electron microscopy or SEM. Provides high-resolution imaging of corrosion products and surface features. Can perform elemental analysis or EDS to identify corrosion products. Optical and microscopic techniques advantages includes. Detailed microstructural insights. Identifies corrosion phases. Optical and microscopic techniques limitations includes. Expensive, requires sample preparation. Inspection and monitoring methods for detecting oxidation damage. Number 8 is surface analytical techniques. Number A of surface analytical techniques is X-ray diffraction or XRD. Identifies crystalline phases of corrosion products such as Fe2O3, CuO. Number B, of surface analytical techniques is X-ray photoelectron spectroscopy or XPS. Determines chemical states of surface elements. Number C, of surface analytical techniques is Auger electron spectroscopy or AES. Provides elemental and chemical state analysis at the surface. Surface analytical techniques applications includes: characterize oxidation layers and corrosion products. Inspection and monitoring methods for detecting oxidation damage. Number 9 is non-destructive monitoring technologies. Number A, of non-destructive monitoring technologies is corrosion coupons and probes. Expose small samples or sensors in service environments. Measure corrosion rates over time via weight loss or electrochemical signals. Number B, of non-destructive monitoring technologies is electrochemical techniques. Potentiodynamic polarization, measures corrosion potential and current. Electrochemical impedance spectroscopy, EIS assesses protective film integrity and corrosion rate. Number C, of non-destructive monitoring technologies is corrosion sensors and embedded monitors. Sensors embedded into structures provide real-time corrosion data. Examples include galvanic sensors, fiber optic sensors, or RFID-based systems. Inspection and monitoring methods for detecting oxidation damage. Number 10 is advanced and emerging methods. Number A, of advanced and emerging methods is thermography, includes: detects temperature anomalies related to corrosion activity. Number B, of advanced and emerging methods is acoustic emission monitoring. Detects sound waves generated by crack formation or rust spalling. Number C, of advanced and emerging methods is laser-induced breakdown spectroscopy or LIBS. Elemental analysis of corrosion deposits. Number C, of advanced and emerging methods is remote and continuous monitoring. Use of wireless sensors and IoT devices for real-time data. Summary table of oxidation damage mechanisms inspection and monitoring methods. Visual inspection method is to detect surface rust, cracks. Then, the advantages of this method is simple, quick. The limitation of this method is only can detect surface only. This method's typical use cases is in routine maintenance. Ultrasonic testing method is to detect wall thinning, pits. Then, the advantages of this method is quantitative, subsurface. The limitation of this method is surface preparation needed. This method's typical use cases is in structural integrity. Radiography testing method is to detect internal flaws. Then, the advantages of this method is internal visualization. The limitation of this method is safety, cost. This method's typical use cases is in internal corrosion detection. Eddy current testing method is to surface or near surface flaws. Then, the advantages of this method is portable, fast. The limitation of this method is limited depth. This method's typical use cases is in coating defects, pitting. Magnetic particle testing method is to surface flaws in ferromagnetic. Then, the advantages of this method is sensitive, portable. The limitation of this method is material limited. This method's typical use cases is in surface crack detection. Liquid penetrant testing method is to surface cracks, pits. Then, the advantages of this method is easy, inexpensive. The limitation of this method is surface only. This method's typical use cases is in surface defect screening. Microscopy method is to microstructural details. Then, the advantages of this method is high resolution. The limitation of this method is costly, destructive. This method's typical use cases is in research, failure analysis. Electrochemical method is to corrosion rates. Then, the advantages of this method is quantitative, real-time. The limitation of this method is complex setup. This method's typical use cases is in monitoring corrosion activity. Sensors probes method is to detect continuous data. Then, the advantages of this method is real-time, remote. The limitation of this method is cost, calibration. This method's typical use cases is in structural health monitoring. Oxidation damage mechanisms inspection and monitoring method. Final remarks. Effective detection of oxidation damage relies on combining multiple inspection and monitoring techniques tailored to specific materials, environments, and damage severity. Regular inspection schedules, combined with advanced sensors and analytical tools, enable early detection, targeted maintenance, and prolongation of structural service life. Thank you.